This week we're going to look at two more applications, sort of real-world applications involving a system of equations in two variables. Now again, all of these scenarios could be extended to multiple variables, and these are not the only applications of systems. These are just a few different ways to show you how these might apply in different contexts. So the first one we're going to look at today is uniform motion. So you might see this in physics or definitely engineering if you're involved in travel, whether it be as a pilot or a Navy captain or something like that. These are all things that you're going to have to take into account. So what we've seen is that if an object moves at an average velocity v, the distance s covered in time t is given by the formula distance equals velocity times time. So that would be s equals vt. Now, you probably learned this formula before as d equals rt, distance equals rate times time. Now, remember that your rate, aka your speed, is always going to be a scalar. Velocity can have direction. A positive velocity means it's going one way. A negative velocity means it's going another. And then this idea of seeing s to represent the distance is really common in calculus. And the reason why we use s is, I believe, that it is from the Latin word spatium, which means distance, or location or position. And so anytime there's a weird sort of letter used, it's usually because it connects to Greek or Latin. And so this is more the relationship being a little bit more precise in its meaning than distance equals rate times time, but it is the exact same thing, okay? So objects that move in accordance with this formula are said to be in uniform motion. Again, it's important here that we're talking about the average velocity because, if you put your foot on the gas pedal, very rarely do you keep that at a constant velocity, like you put more pressure or less pressure depending on what happens. So we're looking at just the average velocity over that interval. So that's important too. Wind, water current, and all kinds of other forces are going to have the effect of increasing or decreasing a traveler's velocity. If the wind is blowing straight at your car, you have to work harder to make it go faster. And when you travel like on an airplane, usually either the flight there or the flight back is significantly shorter than the other because the wind, if you get a tailwind, is helping to increase the velocity of your airplane versus a headwind, which is slowing your airplane down. So what we want to look at is how that is going to affect our travel. Okay. So here's an example. When a small airplane flies with the wind, meaning it's going the same direction as the wind, it can travel 450 miles in 3 hours. When the same airplane flies in the opposite direction against the wind, it takes 5 hours to fly the same distance. Now let's tie this back, just because you all kept asking me about this, to what we know about vectors, okay? We said velocity is a vector. So if I have the velocity of my airplane, okay, that's my vector of the velocity of my airplane. And then I have the wind. If I'm flying with the wind, that means that I'm going the same direction. If I add that vector, now we are going to have our resultant vector is going to be this whole thing. So it increases the velocity if I'm flying with the wind. Now, think of what that would mean if I'm flying in the opposite direction, okay? If I am flying, say, this way, that's my airplane, and the wind is coming in the opposite direction of me, then what we're actually doing is subtracting, and that is shortening the length of our vector. It's slowing our airplane down because that force is acting opposite of the velocity of the airplane. So this is why it's important to talk about velocity not just like speed or the general rate. The direction that we're going matters here. So, we want to know when the same airplane flies in the opposite direction against the wind, it takes 5 hours to fly that same distance. So the distance is 450 in both directions. We want to find the average velocity of the plane in still air. So if there's no force acting upon it, what is our velocity? And then we want to find the average velocity of the wind. So what is that force that's acting in opposition to our airplane? Okay, so I always say when you're trying to define your variable, I got cut off. Look at the question. What is it asking us to find? So it is asking us to find the average velocity of the plane and the average velocity of the wind. So we're going to let those be our variable. Let's have x equal, X is going to be the average velocity of the plane when it is in still air. And then we're going to let y equal the average velocity of the wind. Okay, so those are our two unknowns. And those two kind of act in tandem with each other. Now, again, I'm just presenting a strategy for you here, but it really doesn't matter how you want to set this up. I'm going to organize this information into a table again. So we have two different things that we are looking at. We have the trip with the wind, and then we have the trip against the wind. So there and back. And then, against. The three things that we need are the distance, S, we need the velocity, and we need the time. So we know that when we multiply velocity and time, we're going to get distance. So that's how I'm going to organize this. We have our velocity, we have our time, and then we have our distance, okay? That's how I'm going to organize this information. So the trip with the wind, kind of when we talked about the vectors, the wind is going to help the airplane to go faster. So the velocity of my plane is going to increase according to the velocity of the wind. However, when we're working in the reverse, the velocity of the wind is going to take away from the velocity of the airplane. So it's going to be x minus y. On the way there, they told us that it took us 3 hours to travel. And on the way back, they told us it took 5 hours to travel. Now, according to the rule then, the distance should be 3 times x plus y. And here, the distance should be 5 times, x minus y. But we also know something about that. We know that that distance is 450 miles in each direction. So that's how we're going to set up our system. We're going to take this information, and we know that I'm going to go ahead and distribute 3x plus 3y. That distance is 450 miles. We also know that 5x minus 5y is also equal to 450 miles. So there's our system. Now you need to decide if you want to use substitution or elimination. I look at this and I don't see a variable with a coefficient of 1, so I'm going to go straight to elimination. But there's definitely a case to be made here for substitution because those are going to divide out nicely. You're not going to get any fractions, but I still would probably stick with elimination. I already have y's with opposite signs, so I'm going to multiply this one by 5 and this one by 3. And when I do that, the system I end up with is 15x minus 15y equals 2,250. And then I get 15x plus 15y. Hold on, I've got those backwards. I couldn't see part of my screen. This one is positive. This one is negative. And that equals 1,350. Now we're ready to eliminate. So I will add these together. My opposites divide out, and we get 30x equals 3,600. And when you divide by 30, we get x equals 120. So x is the velocity of the plane in still air. Now we need to figure out what's the velocity of the wind that's either helping us or hurting us. So the velocity of the wind, we need to solve for y. So I'm just going to take this value and plug it back into one of our equations. Doesn't matter which one, I'm going to pick the one with the 3's. So I have 3 times 120 plus 3y equals 450. 3 times 120 is 360, and so when I subtract 360, we get 90 equals 3y. So that tells us that y is equal to 30. Now again, this didn't ask us to solve for x and y, it asked us about something in a context here. So I'm going to go ahead and write my answer using correct units. And so that's what we get. So if we think about what this does, when I'm flying with the wind, that's the equivalent of my plane really going 150 miles per hour speed. If I'm flying against the wind is subtracting from my velocity, so it's the equivalent of only going 90 miles per hour. That's why it takes longer to go the second way, because the wind is slowing you down. So that is an example there. So what I would like for you to do is to see if you can define your variables and set this one up yourself. It's very similar. So this one says, with the current, a motorboat can travel 84 miles in 2 hours. Against the current, it's like trying to walk upstream is a lot harder than swimming downstream. The same trip takes 3 hours. Find the average velocity of the boat in still water and the average velocity of the current. So I want you to define your variables, because that's the most important part, and then see if you can come up with your system there. Go ahead and put the video on pause, and I'll give you just 3 seconds before I show you the information. So your variables should be, I chose X and Y, and this is the order that I chose. X is the average velocity of the boat when it's in still water, and Y is the average velocity of the current. When you set up your table, when we kind of capture our information here, the trip with the current is going to have an average velocity of X plus Y. The velocity of the current is going to increase the velocity of our boat. The time is 2 hours, and the distance is what you get when you multiply those two. Similarly, the trip against the current is going to take away from the velocity of the boat, X minus Y. That takes 3 hours this time, and that's what we get for our distance. Now, to build our equations, we need to use the fact that we know the trip that we're taking is 84 miles, and it's 84 miles one way and 84 miles to get back to where you started. So they're both going to be equal to 84. So here's the system that we should be solving. And once again, this is another one where I thought that using elimination would be the most efficient. And so I did that, and the answer that you should get, I'm pretty confident you can solve a system by now, is that X is 35 and Y is 7. So don't forget now that we need to interpret that in the context of our problem. And that is to say that the boat in still water, if we're being very specific, has an average velocity of 35 miles per hour. And then the current has an average velocity of 7 miles per hour. So once again, when you're traveling with the current, you're really going 42 miles per hour because the current is increasing your velocity versus the way back, which is only going to be, 28 miles per hour. So that is how you can use systems of equations to solve uniform motion problems.